Let's start the module on choice under uncertainty. I'll begin by talking about expected value and variance in this video. The next video we'll actually get to the theory of expected utility. All right, let's motivate this topic. The general heading here is risk sharing. And we can think about it by asking the question, what is it that insurance does? And here's a picture on the right-hand side of a house that's burned down. What's that meant to signify? Well, of course, it's an unhappy event. But what it also means is that a lot of wealth has been lost. And we can think about, we face in the world these uncertain prospects where we might have different amounts of wealth in different states of nature. People in general don't like to face that kind of risk. And so what insurance can do is it can somehow reduce the utility cost of bearing risk. And I want to explain what all those things mean as we go. A second big example, and this will be in a couple of video modules, will be on securitization. Think about risky investments. So one kind of risk is like the risk that an investment might not pay off. Now that risk can be so unpleasant to face that that investments that we had ought to do don't get undertaken. But there's a question about what if we break them into small chunks? That's what securitization is. That is securities, owning securities as opposed to undertaking enterprises on one's own. Maybe that makes the risk-bearing cost bearable, and maybe we see investment. So anyways, that's the broad motivation for this topic, but let's jump in. All right, so what we're talking about here is choice under uncertainty. Up to now, we've been talking about choice with certainty, so we had a theory about consumer theory, utility functions and so forth, where individuals had, utility over, say, 3 apples and 4 oranges, and those were 3 apples and 4 oranges with certainty. Now, instead, we're going to summarize the thing that you could have as simply one dimension, wealth, but the issue is you don't know how much wealth it's going to be. So to make this clear, let's think about jobs in 2 states of the world, where states of the world are things that could happen. So for us, these things that could happen is that the economy could be going well over here, the economy's good, or the economy's going badly, so the economy's bad is another state of the world. And let's suppose there are 2 different jobs that have sort of different payoffs in different states of the world. So the first job we'll call sales, and that word is just meant to suggest that it's sort of risky. Now the possibility that the economy is bad, let's say that has a probability of 0.5. That's not a job-specific feature, that's just about the macroeconomy, whereas the probability that the economy is good is also 0.5. These 2 things sum to 1. Either the economy is good or it's bad. Now if you have the sales job, when the economy is bad, your pay is $500. When the economy is good, your pay is $1,500. So a big difference in your pay between those 2 states of the world. Then let's think of a job that we'll characterize as being government, and that just means is meant to convey that it's sort of less sensitive to good and bad states of the economy. And let's say that your pay in the bad state of the world, if the economy goes badly, you get paid $900. If the economy goes well, you get paid $1,100. Okay, so all this table is meant to do is to say, here's how to think about 2 possibilities. You could either have this job or this job, and 2 states of the world. The economy could be bad or the economy could be good. And depending on which choice you had made, whether choosing sales or government, you'd have these different potential payoffs, 500 versus 1,500 or 900 versus 1,100. Now, having laid out those possibilities, we want to figure out some ways to characterize those payoffs, those 500s and 1,500s and so forth. First definition I want to introduce is called expected value. So what expected value is literally just the average of the outcomes, but weighted by their probability of occurring. So to see this idea, let's imagine a little coin flip game. And here's how this game works. It pays $1 if the coin comes up heads. It pays $0 if the coin comes up tails. Let's say it's a fair coin, so it comes up heads and tails, half, 0.5 or half the time for each. Let's suppose you were to play this game 1 billion times. Well, what would happen is you'd win half the time. That's sort of a way to think about probabilities if it's not already clear. So what is it that you expect to win? Well, what you expect is the probability that tails occurs times 0, because that's the payoff if tails occurs, plus the probability that heads occurs times 1, which is the payoff if heads occurs. So what is that? Well, it's $0 times 0.5 plus $1 times 0.5, and it equals 50 cents. So what we would summarize this just by saying the expected value of your winnings in this game would be $0.5 or 50 cents. All right, let's take this expected value idea back to the jobs. So how's this going to work? Well, we want to weight up these potential outcomes. For example, the sales job has one potential outcome, which is 500, another potential outcome, which is 1,500. The probability that you get paid 500 is 0.5. The probability you get paid 1,500 is 0.5. So what we could do in general is just say the expected value of x, this outcome, is the probability that x equals this particular x, x1, times x1, plus the probability that the x equals this other particular x, or x2, times x2, which we could summarize here as P1, the probability that outcome 1 occurs, times x1, plus P2, the probability outcome 2 occurs, times x2. Now here, because there are just these two outcomes, 1 and 2, the probabilities of those two outcomes sum to 1. So we could also just say that P2 equals 1 minus P1. Maybe the best way to see it is just to go straight to the example. So let's look here at the expected value of job 1. Job 1, again, is the sales job. So what is that expected value? Well, it's 0.5 times the outcome in the bad state plus 0.5 times the outcome in the good state. 0.5 times 500 plus 0.5 times 1,500 equals 1,000. Let's now also consider the expected value of the second job. Well, that's 0.5 times the outcome in the bad state, which with the second job is 900, plus 0.5 times the outcome in the good state, which again with the second job is 1,100. The expected value of the second job also equals 1,000. So it's sort of interesting. They both have the same expected value. Now, I often ask people, all right, they have the same expected value. Which one do you prefer? Most people, not everybody, but I'd say the vast majority of people say, I would prefer job 2 because it seems in some sense less risky, right? So the worst thing that could happen to me is much closer to the better thing that can happen. You know, whereas with job 1, worst thing that can happen to me is pretty far from the better thing that could happen to me. And again, most people prefer job 2. Well, we've seen a suggested notion of risk just in sort of gap between the worst and best thing that can happen. What I'd like to do in the next slide is just formalize our notion of risk a little bit. Now to do this, let's consider the gap between the outcome, which in the previous slide, the outcomes, for example, with job 1 were 500 or 1,500. Let's consider the gap between the outcome, the particular outcome that can occur, and the expected value of the outcome. Now, what we'd like to do is to sort of think about the size of that gap. Like, what's the average size gap we're going to experience? But we have to do a little bit of dancing to make that make sense, so let's do that. We want our gap measure, like this average gap measure, to be positive. And so in order to make sure it's positive, what we'll need to do is square it. So let's square the gap. And then what we'll find is the average or expected squared deviation. And that's what we're going to call variance. Okay, now variance is going to help us answer the question about risk. So that's where we're headed here. Right, so here we are. We're looking back at these jobs again. And now what we have in these tables, we have job 1, we have the probability of one state occurring, and we have now the gap in that state. We have the probability of the other outcome occurring and the gap in that state. So this is in the good state with job 1, you're 500 above the expected value. With job 2, in the bad state, you're 100 below the expected value, and in the good state, you're 100 above the expected value. Now, you could just sort of stare at this upper table and say, what would happen if I just tried to take the average gap along row 1? It would be 0.5 times minus 500 plus 0.5 times plus 500. These would cancel. You'd end up with 0. So you wouldn't really get a measure of the average gap. You'd just get 0, and you'd get the same answer with the second job. 0.5 times minus 100 plus 0.5 times plus 100. So the expected gap, just plain gap, isn't going to be a useful measure. But as I said, if we square things, we make everything positive by squaring them, then we're going to get somewhere. So now let's think about 0.5 times now minus 500 squared plus 0.5 times 500 squared. And similarly, we could think about for job 2, 0.5 times minus 100 squared plus 0.5 times 100 squared. Well, now we're going to get somewhere. So when we take the expected values of these gaps, now what we'll have is variance. So let's do that explicitly on this slide. The variance calculation is weight the squared gaps by the probabilities of occurrence. So what we're doing is, and this is just reproducing the table we had before, so let's jump down here. Sigma squared is just some notation we use for variance. So sigma squared for job 1 is the variance of job 1. That's just kind of a definition. So what is it? It's 0.5 times minus 500 squared plus 0.5 times plus 500 squared, and the answer is 250,000. What about job 2, which remember was the so-called government job where there was less difference between the worst and best outcome? Now we have 0.5 times minus 100 squared plus 0.5 times 100 squared, and that equals 10,000. What you see is that job 1 has a much bigger variance, 250,000, much bigger than 10,000. Remember, both of these jobs had the same expected value, but one has higher variance, job 1, and that was the one that we intuitively felt was riskier, and the fact that it has higher variance is a confirmation, given that it has the same mean, that it's riskier. All right, so let's just sum up where we've been so far. We've introduced a couple of ideas. One is expected value. Now that's just the probability-weighted sum of the values of the outcomes. So it's just the average, or what you on average expect to happen. The variance, though, instead, was the sum of the squared deviations from the mean, or think about it as the expected value of squared gaps. Okay? And the idea is that more variance with the same mean is more risky.